Welcome to our presentation on leading multi-agent teams to multiple goals while maintaining communication. This research was conducted at the Colorado School of Mines in partnership with the U.S. Army Research Laboratory. We are addressing the problem scenario where robot leaders must guide a group of followers to multiple locations while leaders maintain communication with each other and their followers. We propose a principled approach based on regularized optimization that balances advancing towards goals and communication maintenance. We then introduce an iterative solver, which we prove is theoretically guaranteed to converge to the optimal solution. We formulate this scenario as a problem of balancing competing utilities. First, shown in the left figure, leaders must make progress towards goals. The leader in the red must make progress towards the goal in the black. Next, shown in the middle figure, leaders must maintain communication with their followers. Finally, shown in the right figure, leaders should also maintain communication with other leaders. We formalize this as an optimization problem, where we find weight matrices W, V, and U that optimally balance these different utilities at each time step. In order to control the weights that balance these competing utilities, we introduce constraints and regularization terms to integrate expert knowledge about how leaders should operate. First, we restrict all weights to be non-negative. A leader should not be able to negatively value a goal or communication connection. We also define that for each form of utility, the weights for each leader should sum to 1. That is, for each leader, the weights distributed across all available goals should sum to 1, the weights across all available followers and all available other leaders should all sum to 1. Next, we want to encourage leaders to make progress towards only a single goal at a time. If a leader splits their attention among multiple goals, then progress towards any single goal will be slower. We introduce a norm that applies the L2 norm on each row of W. With our introduced constraints, maximizing this value results in limiting weights to only a single goal for each leader. We also introduce a regularization term to reflect the fact that no more than a single leader should value maintaining communication with each follower. To do this, we again utilize an L2 norm, but on each column of V. With the introduced constraints, maximizing this value results in only a single leader assigning value to maintaining communication with each follower. Finally, we introduce terms to enforce temporal consistency. Temporal consistency ensures that leaders not make sudden changes in their movements, as this results in slower progress. That is, if a leader is progressing towards one goal and makes a drastic change to move towards a second instead, then the initial progress may be lost. To enforce this, we introduce terms that penalize the difference between weight matrices at the current time step and weight matrices at the previous time step. Combining these introduced constraints and regularization terms results in this final optimization formulation. Solving this final formulation finds an optimal balance at each time step that enables leaders to make progress towards goals while maintaining communication with followers and fellow leaders. As this formulation is hard to solve due to the constraints and non-smooth terms, we introduce an iterative algorithm which is proven to converge to the optimal solution. This algorithm can be found in our paper. We then use the optimal weight matrices W, V, and U to generate position updates for each leader. This video shows a simulation of our approach. Red circles represent goal positions, black squares represent leaders, and green triangles represent followers. As the simulation begins, we see the left and right leaders moving up as they move towards the outer goals in order to maintain communication with the centrally located leader. As each leader nears a goal, we see the balance in progressing towards a goal versus maintaining communication. Here, we present quantitative results from a repeated simulation. We consider 3 scenarios with progressively larger complements of leaders, followers, and goals. Scenario A is the smallest, and Scenario C is the largest. We compared our full approach to a baseline that did not utilize or introduce regularization terms, a greedy algorithm where leaders only considered progress towards goals, and a random approach where leaders moved randomly. We see that our approach led followers to goals significantly faster than other approaches in the graph on the left, and completed simulations with a much lower average follower to goal distance in the graph on the right. We also evaluated our approach in a high-fidelity simulator in order to integrate it with ROS. The left figure shows the initial state with 2 leaders and 6 followers. The middle figure shows these robots progressing towards goals, and the figures on the right show them arriving at goal positions. Thank you for coming to our presentation. We introduced the problem of multiple agents leading followers to multiple goal positions while maintaining communication. If you have any questions, please feel free to email any of the authors. Thank you.